So like Shrubbery is the proposed like next generation application model for Urbit. When I say it's application model, I'm like kind of lying. It's not really an application model, but it's like a thing that's supposed to replace the application model, because like applications are bad for a variety of reasons that I will get into later. So like I think the first question about like a new application model for Urbit is like, okay, what is Urbit? Okay, Urbit is like a purely functional operating system. It's like peer-to-peer, it's decentralized. You get a whole bunch of things for free when you build on top of Urbit. So number one is like you have referential transparency across a global namespace, which means there's like you can have some like name that is like globally valid anywhere in the like Urbit system, and it's like you'll know how to retrieve that data, and it will always be the same, like no matter where you retrieve it or anything like that. You also get exactly once delivery for network messaging, and a public key infrastructure for like all of the nodes, all of the like computers like in the network to talk to each other. So what is like Shrubbery as such? It's the next generation application layer, but it's also all of these things. So we have like, it is basically like message passing OOP. It is also like a build system, and indeed like we use the affordances that we get from Shrubbery to move the build system in Urbit from the kernel space into the user space, which also allows you to use other languages like like Haskell or Node or whatever inside your Urbit, instead of being like limited to the like Hoon that we like currently use to write the kernel and the compiler and so on. It's also like an FRP style environment. You can like subscribe to different parts of like the namespace and like react to those updates. We also have a way to like basically back an EAV database out of this application model while also retaining a lot of the niceties of like SQL style databases. Okay, so what's in it for the user? Like, why would you actually want to use a system that's built like this? So basically this allows like polymorphism to like bubble all the way up like to the user layer. And so like because of like you have this kind of polymorphism, like basically it's impossible to sort of like have any kind of like vendor lock-in, because whenever you're like communicating between software components, that's always being constrained like basically by the external interface, which anybody else is like free to re-implement and can like, basically you can re-implement that. And so like what you can do with that is like have, for instance, like chats, instead of like, a chat is like, it's like has like a static like chat message data type inside of it, you can actually have like a user level chat that's like polymorphic over the kind of message that's being sent in it. So like it doesn't matter, instead of like, you can have somebody like define some kind of message type here and some kind of message type there, and it's like, so long as they both like look like messages to the chat like application, then it's fine. And so this like basically prevents any kind of like lock-in from creeping into the system, and allows you to like actually like own your data in a way that's like, well, I just need to like find something else that implements that like protocol, and then it's fine. You can just always universally like move your data. All right. What's in it for the developer? So like because you can do this, you can like, it's like very easy to like reuse like software components, right? It's like, oh, if I want to like send payments or something like that, I can just like look for somebody else, like the already installed wallet, instead of like having to like ship my own like functionality. We also have some nice tricks around like improving like code reuse, especially across like transactionality layers that I'll get into later, which is fun. I should have taken the coherent security model out. We will get a coherent security model, but I behest that you like do not ask me any questions about that quite yet. Okay, so the Urbit namespace. Like, so Shrubbery comes out of a series of ideas about like, well, we need to move in order to make proper use of this like, really nice like global, statically typed, functional namespace. We need to put our application model inside of it. Now, so in order for me to tell you about what that is, I need to first we need to go through the namespace. So at the top of the namespace is this like node ID. This is my node ID. We call it a ship, but I will call it node ID for the sake of not making your brain explode. we have a version number, and we have a path, which is like basically like a HTML, like a HTTP style path, /foo, /bar, /baz, it's whatever. So a name in the namespace is the node ID, which is like basically like the IP address. It's also the user's username, the like point inside that node, and the version number. And so like the namespace itself is just a mapping from these names to pieces of data. And we tag the data with a type ID, which is the type, and that type also lives in the namespace, so you can like query and do all sorts of nonsense on it, but that's not super important right now. And then we also have this idea of a ref, which we use to turn sort of like, to like kind of introduce mutability back into the system. We just drop the version number, and then you can sort of like coherently like reference this thing in the namespace across time and across versions. So we need to understand like the implications for like what this, like /foo, /bar, /baz, what putting an application model inside this, like what that actually means, right? And so like after much head scratching and some hammock-driven development, I came up with this. So any path foo has like some set of ancestors who are like, it's like the prefix, right? So /foo and the empty path are ancestors of /foo, /bar. Descendants, that's all of the children. So it's like, okay, foo bar baz and foo bar crocs are the descendants of foo bar. It's pretty, relatively easy to wrap your head around. Okay, so axiom 0, constraint. A shrub is code that is designed to constrain the namespace. It's like, in order to be able to program against the namespace, you want to be able to, like, it needs to have some predictable behavior about its future. And so you have to constrain the way it, like, updates, like, in the future. And so when you do this, because it's hierarchical, like, a shrub should both constrain the path of the data that lives at the path and all of the data that lives underneath it. Axiom 1, relocatability. So shrubs basically like, they treat children like sort of in this like kind of recursive fashion. It's like the children is like the children, which is to say like the shrubs underneath you is really all you know about from the perspective of this like shrub. Like you don't know anything that goes on above you or to the side. And so like what you get out of this is this notion of like arbitrary relocatability, right? Because we want this idea of a shrub to replace the idea of a file. It's like nonsensical to have a file that you can't install in like certain folders. Like a file needs to be like universally relocatable. And so it's like, if it's universally relocatable, then like you get a whole bunch of really nice compositionality properties out of it for free. Okay, transactionality. So like Urbit, amongst other things, is like an ACID database, and it really, really cares about like valid state updates. And so like it should not in the general be possible in the process of like, combining and composing your software for like, an invalid state transition to somehow become cemented in the state of the namespace. So given Axiom 0 and 1, that like each shrub is its own like recursive ACID database. Like it has this, this zone of like consistency that like kind of telescopes down to each of its children. You can have like sort of foreign key relationships with the children, and like you are responsible for like sort of maintaining those. Now, Axiom 3 is like, okay, so when you have a shrub and you like make children on them, each of those like shrubs is like the path to that shrub is a primary key. Treat it like one, which means like, use surrogate keys if you have to, all of that kind of nonsense. Like standard sort of like relational database kind of things sort of apply. All right, so like the tension between like having like everything be like maximally like transactional and the like everything be discretely addressable is like how you sort of learn to separate out what goes at this path and what goes underneath this path, right? And this sort of like getting a hold of that is the sort of one of the like key skills that you acquire like as you work with this system. And so like you really need to sort of like lay things out in such a way that you have like really optimal like transactionality guarantees, and so that all possible invalid state transitions are forbidden, basically by construction. So if a container is like, if you have like a chat of messages, it's like, okay, you put the messages in the children because you need to have like a primary key for each of the messages. If you want to reuse functionality for the same reasons, you kind of also like pull it into the children. You also pull things into children if you might have to version them differently. I'll talk about that later. It's quite nice. But like, if you have some kind of like circular like data flow dependencies, that needs to be sort of hoisted up into the parent. So we have like kind of an example of this. You can see it's like a chat message, like a chat sort of demo. So like inside the chat itself is like, okay, the set of nodes that are allowed to post to that chat, a title, the ID for the pinned message, and then inside of that chat you have like a bunch of messages which are their own shrubs that have obviously like who sent them, what's in them, when they got sent, so on and so forth. We're skipping over those. All right, this is the external API. This isn't Haskell. The actual system is in Hoon. I felt like going easy on you. So we have the type of the state is just declared to be like the type ID, which again is just another like thing in the namespace. The type of messages is a set of the like type ID, which is like, okay, I can receive any of these messages basically. I will like validly like transact on those. A path pattern is like, it's kind of like a route binding, sort of like if you're familiar with like HTTP routes. It's like, okay, /foo, and then any argument, and then baz. So it's like you can constrain like the parts of the children to be different. And then so we have the whole Shrub API is just, what's the state type? What messages can I get? And what are my children supposed to look like? And the children are a map of like, again, the pattern match over the path to another Shrub API. So that's it. That's the whole like external interface for like programming this thing. So this is just message passing, like in kind of a like small talk or like whatever your favorite message passing like hobby horse to beat is. Like it is just message passing, but it's like recursive, and we can leverage this like recursive sort of message passing to do some fun tricks. So, right, just like another aside on like this perspective, it's like, okay, sometimes you care about the thing at the path, the thing and its immediate children, or the whole subtree underneath it. And so, this is like what this is what the sort of implementation like of the shrub looks like. So you have a message which is a reference to the namespace, so without the version number, the type ID of the message, and then some like dynamic data. That dynamic data depends on the type ID, and you can kind of conceptually think about this in terms of like a giant tagged data union where the tag is the type ID and like data.dynamic is the like actual sort of resolved type of that thing. This is like kind of an idea that you can't really express with Haskell, so it's just data.dynamic there. Okay, so the response to a message is a list of more messages to send and the new state of the shrub. Okay, and then so we have handle message is from context, and it takes the message and it produces a message response. Context includes a bunch of things like what the children look like, and like entropy and other like where you are in the tree and all that kind of shit. And then, so this is where it gets fun, is because like relocatable shrubs in the general like need to have some way to escape their position in the namespace. So like what we do in order to allow this is like every shrub can declare a dependency on any other number of shrubs. And so we have here's an example, right? So a notifications inbox is something you canonically want one of. If you have 10 notifications inboxes, that's not that's not a notifications inbox, that's just fucking email. Like, you canonically need one. And so like the way you would do this is that every time you make a chat shrub, then that would take the notifications inbox and have that be injected so it knows where to send notifications. And then for the same read sort of thing, it's like if you want the chat to take some idea of what the access control for that chat is from somewhere else in the namespace, you can again do this as a dependency. And so if we go back up here, you can see the dependencies here. So it's like a map of string that just this is a wallet, this is an inbox, this is whatever, to the perspective and the what you want the shrub to look like. And so note that it's structurally typed here. So it's like you're declaring the kind of dependency you would want, but you're not actually saying oh, I want this specific implementation or whatever. And because you can do that, you have an opportunity for sort of kinds of polymorphism here, because it's you can basically do structural subtyping. Okay, and so foreign synchronization, this is also how you do foreign, kind of sort of trivially, this sort of follows that the way you synchronize from other nodes is that you also inject it as a dependency. And so we have a whole system for it's okay, if you inject a dependency, it will basically by the time that you see the shrub boot up, it will already have all of that foreign data synchronized and ready for it, and you don't have to deal with diffing or management or version management or anything. It will just be there for you, and it will be there exactly the same as any data that's already on the node. So it's from the perspective of the developer, the foreign data and local data is no longer that meaningful of a difference. Okay, reactivity. So you can basically you react to changes in the dependencies, and so we use this to build the build system with that same dependencies technique. And so it's the build system is kind of the whole thing. So yeah, you can use this for a variety of things, get woken up when your wallet gets paid or that kind of stuff. Okay, so here's the fun thing. The children are also have this kind of structurally subtype polymorphism in them as well. And so what you can do with this, I'll get onto that later, but it is fun. So Urbit really cares about transactionality, as I've mentioned before. But this is an FRP system, and so one of the classic issues with FRP systems is that when you use them in a sort of ACID database context like this, that you're coupling the unit of transactionality and data consistency to the unit that can be reacted upon. And so this produces basically there's too much reaction going on in the system, and you end up with performance issues because you're basically doing redundant computing. So our solution to this is actually really nice. So if you send a message down the namespace, so to your children or to their children, this is basically this acts like a function call basically. And so it will happen if you crash anywhere when you sending messages to your children, the whole event will reject, and all of the everything so far that's been handled in the event will be totally rolled back. And so because of this, you can reuse from the perspective of the parent, when you reuse something for children, you have function call semantics into those children. But if you're sending messages to your dependencies or anywhere else, that's an asynchronous message pass. Partly, and you will receive an acknowledgement when that does happen, because potentially when you do something to a dependency that could live somewhere else on the thing, somewhere else on some other node. So yeah, and so this basically allows us to sort of kind of split the difference between externally calling an API and calling into a function. Depending on the way you look at it, it's all just a message pass. And so we just don't have those same kinds of problems because you have this these nested transactionality boundaries. Okay, so here's a worked example, right? So if I poke chat and then the chat decides to do something create a message and then sends a message to one of its children, and then that crashes, then any changes that we made to the chat just then all get rolled back. And so this telescopes sort of all the way backwards. However, if the chat does create the message successfully, and then it's like, okay, we should wake the user, we should tell the user there's a new message, it will send a new notification message to the notifications dependency, which has unfortunately been cut off here. And then that will get an ACK back. You will actually get a manual acknowledgement. You don't get manual acknowledgements with these things because it's kind of implied by the crush semantics. You can always just treat it as if it's already been ACKed. And so yeah, this is kind of one of the cornerstones of the system because it allows you to sort of it allows for kind of compositionality across transactionality boundaries, which is really important when all of the software you're building is implicitly in an ACID database and must be transactional all of the time. Oh, transformations. Okay, so the structural polymorphism system has this notion of transformations, which is it's just you can register functions that convert from one type, and that type has a type ID in the namespace, to another type which has a type ID in the namespace. And so you can use this basically to do kind of something kind of a little bit like ad hoc polymorphism. It's kind of Rust traits or some other generic nonsense. So where this gets fun is in the sort of versioning story. So because Urbit is obviously a decentralized system, right? And say you have some new chat message type that you would like to roll out to your users. What we used to do, and what I was responsible for doing, was you would basically do live type upgrades over the network, and it was absolutely insane. Because if you've ever done database migrations, they're a huge pain in the ass. And it's try doing 2,000 database migrations on 2,000 different nodes, and you can't SSH into any of them because they're everybody's private fucking computer. And it's just not fun. So the solution to this, obviously, is just not to do live type upgrades over the network because they're really, really difficult to get right. And so this is where the polymorphism over the children comes in. If you decide that you have your chat application and it's running on the network and everybody's happy with it, and you decide, oh, hey, I need another feature, another field in this message type, what you can do, instead of having to rewrite all your types live, is basically just publish a new message type, right? And then when you publish the new message type, basically because your chat is already polymorphic over some generic message constraint, then you can just have message 1 and message 2 kind of just coexist, and nobody cares. And the other nice thing about this is because the UI system that we have also built on top of this is also itself polymorphic, then from any you don't really care that you have 100 different kinds of chat message living in your chat. It's all the same from the perspective of the chat developer. Right. Okay, we're done with the transformations Redux. It's just too complicated. Okay, because we have this sort of generic Shrub API notion, the implementation that I just showed you was one thing, one of the ways in which you could kind of implement something Shrub related. And so you can kind of hack this in a bunch of really interesting and weird ways. So the fun stuff is overlay namespaces. So consider some function that takes, well, this should take a type ID data dynamic and a type ID data dynamic, so they're both sort of in that big algebraic data type in the sky sort of thing. So if you mount this function f at transform, then you can have this idea of an overlay namespace, which is a namespace that wraps some inner namespace and transforms it. So if the value of transform /foo/bar is the value of /foo/bar after you apply f to it. And so you can compose this so you get transform /foo/bar, which will obviously apply f twice. And so One of the things that's really nice about this is that every time you kind of recurse on the namespace is another opportunity for for the runtime to sort of like cache the that inner namespace thing. And so like you can basically do like arbitrary queries with like a lot of caching very trivially. And the other nice thing here is that like if you hypothetically had like zero knowledge proofs, not that anybody's working on that, you could actually like have these like overlay namespaces be like kind of calculated for you, and like they come pre-bound and the proof with them, so that you can just like kind of have this kind of ambient compute cache wherever. So yeah, we use this for like dynamic query patterns. So it's like, this is actually how the interface system works. Is we have a whole system for like basically turning any part of the namespace into HTML. And so you can just go for any given part of the namespace, you can just go /HTML that part of the namespace, and you will get that part of the namespace rendered as HTML. This is like sort of again how the build system works under the hood. Is the like you just have like a AST sort of overlay namespace that will just take any like the string the file as a string and then return the like AST of it. And then so you can do more dynamic querying stuff. If you don't want to like overfetch or do anything like that, you can have like, okay, I want the 20 latest children of /chat/messages. And like if you then if you then shoved that into a HTML like overlay namespace, like it all just works. And so the other nice thing here is, so in all of these sort of like paths that I've been showing and things like that, we've been dealing with this like the reference, right? And the reference is, obviously you've lost referential transparency. But what we do actually is we embed the immutable functional namespace inside of our like kind of mutable sort of hyper namespace in order to like, okay, if you would like to deal with like, pin things to the, to a specific version number or something, you can that just lives at /static. So you can just reintroduce the version number and like pin that to the path. And so like this is really useful for instance, like the build system obviously doesn't want to do live type upgrades from some like, random fucking code that it found like wherever on the network. It wants to like pin all of its dependencies until, like whoever maintains the package or like whoever is responsible for the code basically decides that, okay, we can actually upgrade this pattern. I've reviewed the diff, and so on and so forth. All right. That is, I guess, most of the talk. Are there any questions?
This might be a little bit nebulous, but
Yeah.
I'm wondering, it sounds like some of the reasons that you were talking about that you guys came up with this is that it's kind of a reaction to shipping normal agents on the network.
Yep. Yeah.
If that is the case, is there like a vision of this kind of like being kind of merged into like a typical agent model?
No, the more idea is this is to entirely replace the old model. The old model will be like held onto for quite some time because there's a significant amount of people depending on it. But going forward, this would appear to be like the strictly superior way to do things.
Is it included that you always have a tree?
Is it, sorry?
Do you always have a tree, or could paths end up overlapping at some point down the...
No, so there's no overlapping. So it's always like strictly like normalized into a tree.
The other thing that, so if you go back a couple of slides, I guess. Yeah, one forward. Yeah, so it looks like you've got parts of the path that are code and parts of the path that are arguments to that.
Yeah, basically.
And some of the arguments are singles,
Yeah.
kids and 20, and some of them are paths.
Yeah.
And it seems, how do you differentiate that was like what, 3 or 4 different?
Yeah. So we have like a whole sort of like pattern matching system like against pods. If you want to put multiple pods into like an overlay namespace, which is something you can do, it's just like they have to be encoded in a certain way. And we have like a special like encoding thing for like shoving multiple paths into a into like one path. And so like yeah, in the general, we just like we enforce that like none of these things can overlap, and that like you're just normalizing it out.
How much of that pattern matching is novel versus like HTTP routing systems?
It's like until you get into the like we're jamming several paths into one path, it's like fairly standard. It's like okay, you have an arg here, and you have args there. It's mostly fairly standard. And then once you talk about that, you're doing this like whole sort of like run length encoding where it's like, okay, I know I have a list of paths encoded in this path, and this one, the next one is like 3 of these elements, and then you just, it's like run length encoded basically.
So you have some declare dependency.
Yeah.
Would it be possible to like declare a dependency on the one that depends on it?
Like a secular dependency? Yeah, you can totally do this. I mean, you need to make sure, like, you need to be very careful with it because it's like very easy to like break things. And so like there are basically a bunch of rules. So dependencies are a big sort of like security primitive. So like basically you need to be like very careful about having a system that like makes sure that the way you've laid out your dependencies is like sensical. I mean, it's super powerful, right? Actually, I should show the. I totally forgot I had a demo for this, actually. So with the dependency system, obviously the first thing we built was, obviously the first thing we built was like Excel, basically. So like this is sort of like, it's like fully reactive. You can go and you can write code and reference any of these cells in the spreadsheet, but you can also reference anything in the entire node. So you can reference like how many chats, how many like unread chats that you've got in this spreadsheet, right? Like it can totally, because it's just a path, like a reference that it's looking for, that you can just totally do anything with it.
How do you have security if anything can just read data from anywhere?
Well, so you can't. So the only way you can read data is like through a dependency, right? And so like when you read data like through a dependency, basically, if your parent didn't grant you permission for that if the parent doesn't already have permission for that dependency to like re-inject it, then you have to basically go and ask the user, is this okay to inject this dependency?
So does the spreadsheet just have everything as a dependency? How is it able to?
Well, how's it able to do this is because we haven't implemented the security system yet. Like I said, don't ask me about it. Andrew.
So how much of the engineering hurdles that you've had to conquer and the design choices that you've had to make are orthogonal to the ACID nature and referential transparency requirements? And how many are a direct necessary result of demanding that of your system?
I would say like basically most of it is like sort of, most of the design decisions we've made is like very aggressively steered by like referential transparency and ACID requirements.
So if you took those out, do you think you would still have to deal with these same engineering questions in order to achieve a reasonably good system?
If you took those out, we probably would have had to deal with a bunch of different questions, but like to me, it's like those kinds of like constraints are like what makes it Urbit. Yeah.
So following along on that, so everything in a path is ACID.
Yep.
And anything across paths is eventually consistent?
It's basically eventually consistent, yes.
Is it actually eventually consistent, or?
Yeah, it's eventually consistent because we have exactly once messaging, so it will always, at the very least, so long as there is no long-running network partitions, it will always eventually cohere.
What's each character of your demo doing?
Oh, shit. Fuck, I didn't even write this. I just got one of the guys to. So basically, yeah, so this, oh shit. Please don't tell me my laptop slide. Okay, good. Basically, like this is basically like forcing unwrapping unit. And then it's like you switch on the unit because.
What's the first character?
This is a typecast. This says the whole thing, the whole result of this thing is supposed to be a string, which it obviously.
How do you know it's a string?
That's what the pat T says. This is Urbit for string. Shut up, Christian. And then I have more demos actually. No. It's a MacBook. It's got plenty of time. So we have this, which is really nice. It's like basically like homo-iconic, sort of like I guess you would like it's like a editor for the interface inside of the interface, so you can do a bunch of this stuff. It's like live updating, like with the syntax and everything. And so like the main user space developer who works with me on this, he like primarily does most of his development already like in this system, which is cool. And it also automatically saves to like it saves the code to your Urbit as well, like every time. Jimmy.
The dependencies are all strictly downward.
No. So the dependencies are anyway. The children are all strictly downward.
So when you have something which is bidirectionally updating, was that a bidirectional update or was that just a?
No. It's always like a unidirectional update basically, like from dependencies. If you have bidirectional updates, this is like the whole point of the like Axioms 2 and 3 is that like you should lift any kind of bidirectional output like interaction like to a parent node and just have it be like kind of mediated there. This is sort of like, this is like kind of React 101 hilariously, but like, it's just sort of like minimize the number of like cyclic, data dependencies you have and like lift those up to like parent shrubs. Yeah, please.
Okay, so I understand that it has to be done in the background, or at least it's out in the background. But let's say you wanted to implement bidirectional references, a la.
Oh, Project Xanadu sort of thing? Yeah, so the way you would do like a bidirectional reference basically is just like have sort of like an opt-in message passing system where it's like, oh, okay, like I accept this message that tells me that you're backlinking at me, right? And so like you can just sort of, anybody who accepts those kinds of messages is able to like basically produce a list of people that have backlinked to them. But like that has to like strictly be an opt-in system in order to maintain the like consistency of the system. Anyone else?
What's the difference between a child and a dependency?
So conceptually, like a child is like lives in your transactionality boundary, right? It is like a part, is like a table. It's sort of like it lives inside of your like transaction space, right? Like a failed attempt to change a child will revert the entire transaction. A failed attempt to change a dependency will just give you an error message and says, hey, that failed. Look.
So these examples are all generally just like reacting to a change in one thing at a time.
Yeah.
So how does it work if you want to like bundle multiple changes together in like one commit, like a build system?
Like a build, okay, so the build system does, is it actually, no. The build system does something a little funky, which is like, it basically like builds sort of like a cons list like inside, in the namespace. It builds a cons list in the namespace to sort of like get all your view dependencies like sort of together and like gradually like builds those up. But like that's actually nice because as I said before, each point in the name, every time you like put something in the namespace, that's an opportunity for caching. So it's like if two things share the same like namespace, like if they share the same dependencies, then you can just reuse that thing that's already in the namespace and it's trivial. Yeah.
What would happen if I just put a cyclic dependency in the system today?
Oh, it just infinite loops. It's hilarious, and then you have to like basically like control like you. So I've had to kill 9 it before. It's pretty funny, but just don't do that right now. We will fix it. We will fix it before it goes live. The name. Oh yeah. Oh, it's like a little. It's like a bunch of little trees. That's what makes it nice, right? It's just.
Small prickly tree that you have to trim all the time and maintain with care.
Yeah, care and discipline. This is like the way it should be. You should like. Vinny?
What are you looking at? Give us
This is like an interactive like namespace, like the namespace visualizer. So that's what I was saying, is like the HTML like overlay stuff. Like this is it. This is it being in a browser, like working. Yeah. So this is just more overlay namespaces. Going once, going twice. Ed.
I'm going to revert to how annoying I was at multiple ICFPs and say, you're comparing this to FRP.
Yeah.
Is there any notion of continuous update?
No, we have no continuous time signals. Everything is event-based. We do not do continuous. If you want to do that, do it in some other system. I don't like it. I mean, you can build. It's like pretty easy to build like sort of stream-ish primitives because you have like one of the very first things I wrote was like a pulse shrub that like it updates itself every like 100 milliseconds or whatever. It's pretty easy to build sampledness out, like sampled continuous.
That's a follow-on question. How do timers work? Like, how do I put something to sleep and wake up?
Well, you just have a special kind of shrub that is a timer.
But where is it getting its, how is it special? Where is it getting its behavior from?
Where is it getting its behavior from? Well, like we basically like hand waving the semantics of that like right now, but like basically like that talks to the operating system itself. And like eventually you should like reify this so that like it is the operating system itself, basically. And we're done. Thank you guys.